Hi, I'm Peter Scholze. I grew up in Berlin and there went to a school which was a relic from Soviet times in some sense. So it was some kind of special school with an emphasis on math and the natural sciences, which actually over its existence has produced many quite well-known mathematicians, many actually from doing algebraic geometry more or less. And so also already during my high school years, I got fascinated by algebraic geometry, and then at some point I had to, when I finished school, I had to think where I should be going for my studies, and for some reason I actually wanted to stay in Germany, and then I decided that Bonn would be a very good place to go, and ended up working with Michael Rappaport, who was actually also at the same school. And then in 2007 I came to Bonn. In 2012 I did my PhD, then I was a Clay Research Fellow for a few years, and then became a professor first at the University of Bonn, and now I'm a director here at the Max Planck Institute. Yeah, that's a good question. No, I still think of myself as an arithmetic geometer, even though I'm maybe interested in other things, but my primary interest is still in arithmetic geometry, and I'm primarily interested in the other things because I want to apply them to certain questions in arithmetic geometry. Yeah, but some of my I really feel that mathematics is all connected, and that I'm some of I find it's a lot of fun to sort of fluently change between quite different subjects and connect them, and you can talk to many different mathematicians this way and get new ideas. But my primary focus is still, I want it to be arithmetic geometry. I think my primary goal is understanding, and then everything else is just part of that. And yeah, I mean, understanding something well, often that requires looking at it from a maybe slightly more abstract angle or something like this. So naturally, sometimes you develop some kind of new frameworks in order to better understand something, but often, yeah, the starting points for these are also like very concrete computations or something like this. So, but yeah, so the primary goal for me is really understanding, and maybe more specifically, something I would like to understand is the geometry of a certain space that's somehow, to me, the fundamental space in like arithmetic geometry, which is a spectrum of the integers, which is, since the 60s, known to behave in many ways like a three-dimensional manifold, and there are various analogies in this area that are in many ways quite vague, but at least, yeah, I'm trying to understand this picture better and better. And the Langlands program has become quite vast. Just as an anecdote, like there's certain, I do some research in the Langlands program, but then at some point I was focusing on some other aspects of my work, and this led me then to some almost physics stuff and even further. And suddenly I realized I'm doing Langlands again. So, although I tried to get away, but I guess the original Langlands program, as some of Langlands himself originally envisioned it, is concerned with number theory, so with the rational numbers and so-called automorphic forms having to do with arithmetic groups, where some of which are groups of rational numbers. I mean, maybe you see rational numbers or something like this. But then soon it was realized that because of this very strong analogy between number fields and function fields over finite fields, that was originally emphasized by André Weil back in the 40s or something like this, that much of the Langlands program can be done in more or less exactly the same way over these function fields. And Drinfeld did a lot of work there, but then Drinfeld also realized that as soon as you're in the setting where you actually somehow have a curve over a finite field, you might as well try to do some kind of Langlands type stuff with curves over the algebraic closure, or more generally with curves over any algebraically closed field. And suddenly this really has become much more geometric, because you really have now a curve over an algebraic closed field, and you could even take the complex numbers, in which case you really have Riemann surfaces. And so this is what has become the geometric Langlands program, which is in some sense more geometric. On the other hand, quite a bit more abstract, because the primary objects of interest are one categorical level higher. So when you study just automorphic functions in Langlands' original vision, you study automorphic sheaves in the geometric Langlands program, or even the whole category of these sheaves, and try to describe this whole category. Somewhat more recently, there was a kind of wormhole created between different worlds, because there was the so-called Farc-Fontaine curve, introduced around 2010 by Jean-Marc Fontaine and Laurent Farc, originally because of considerations in Pierre de Koch theory. But Farc had this ingenious idea that you could also try to do geometric Langlands on this curve. And he realized that if one interprets this, one gets basically the local version of what Langlands was originally interested in, which suddenly gave a very strange wormhole between the geometric Langlands program and the original setting of Langlands, at least the local part of it. Yeah, around 10 years ago, somehow Laurent Farc came up with this proposal that one could do local Langlands correspondences in the number field case via this geometric Langlands on the Farc-Fontaine curve. And it's a very natural and an interesting question whether there's an analog of this for global fields, for number fields. And I have some kind of vision how such a series should look like. So basically, it's supposed to adapt the theory of Stukas that Drinfeld introduced in the function field case to the number field case. And this has all sorts of connections also to the theory of motives and Shimura varieties, of course, and lots of other things. And yeah, what I'm somehow trying is to find such a theory of Stukas over spec Z if it exists, which is not so clear, because a priori you're looking for something where it doesn't look like it should exist. So I'm approaching this question from various angles, and some kind of recent progress there is that what Farc somehow suggested only works for non-Archimedean local fields, whereas for the real numbers, the Archimedean local field, it didn't work. But now I also found a version of this that works over the real numbers at least. And yeah, and so it's clear that one needs some kind of rather fancy type of geometry to make sense of this putative theory of Stukas over spec Z, and this theory of analytic stacks and condensed mathematics that I'm developing with Dustin Clausen is meant as a framework where I hope that these spaces might possibly exist, and yeah, and then there are some kind of other approaches that I have towards making progress on these things. But yeah, maybe I can tell one about a collaboration that I think was only possible because of MPI, because you make sudden connections with mathematicians that you wouldn't probably otherwise meet. So in this case, actually inspired by this philosophy of Stukas over spec Z or something like this, there was a certain construction that I toyed around with around 2016 or something like this, which was a version of the so-called Harbiro ring. The Harbiro ring is a certain interesting ring of power series around all roots of unity, which is actually very popular at MPI. So Manin worked on this, Macaulay worked on this, Zagé worked on this. I probably forget some people. I realized, I wondered whether there's a certain cohomology theory taken by his modules over the subunit ring, and I realized that at least for Artin motives, so just for finite extension of Q, I was able to write down what the answer should be, so giving you some kind of Fabio ring of a number field. But when I tried to do something in positive dimension, nothing worked, so I kind of gave up on the idea. But then one day, Zagir and Garofelidis tell me that they would like to talk to me because they found some interesting power series and they wondered whether I might have something to say about them. And they didn't know that I was aware of the Fabio ring, so they first tried to kind of gently introduce me to the Fabio ring, and then show me some more complicated power series where they suspected they should lie in some Fabio ring of a number field, and whether I would have any idea how such a thing should look like. And it was like, oh yeah, I know one. And so yeah, they found explicit elements in these rings that I had kind of given up hope on already. And yeah, this led to joint project that was a long time in the making, because we had to connect perturbative complex Chern-Simons theory, whatever that is, some kind of quantum field theory stuff, to some p-adic stuff, and it's still extremely confusing to me. But in the end, we were able to first give precise definitions and even prove the numerical observations that they made. Yeah, so this led me to completely new areas of mathematics, in particular, like some kind of Chern-Simons theory, and it seems to have some connections to the questions I'm interested in. I'm kind of scared about all of this, but yeah. The thing with eureka moments is that usually you have one, and then 2 days later you realize that it was all wrong. So and then when you finally realize that actually it was somewhat right after all, and then it's, after all these up and downs, you don't remember the original. I mean, I don't know. So I don't know. Another thing I was struggling with for a long time is I was at some point trying to understand something known as topological cyclic homology. This is something that I started to think about because my first postdoc, Matthew Morrow, was actually working on this, and I realized that it might have some relation to some things in p-adic Hodge theory I'm interested in. And so I tried to learn what this topological cyclic homology was about, but I was getting, finding it very difficult, because it uses some kind of so-called equivariant stable homotopy theory, and the algebraic topologists use the word equivariance, it seems to me, in a way which is very different from how other mathematicians use it. And they had something they called equivariance, or sometimes genuine equivariance. And then they had a more naive notion they called naive equivariance. But what I wanted to consider as equivariance was even more naive than that. So they didn't even have a name for such a naivety. But still, this was the level at which I was trying to understand what this kind of S1 equivariant topological Hochschild homology was about, and trying to do some computations. And after a lot of these computations, I suddenly realized that there was some kind of pattern to it, and I realized that maybe using just some very naive structures in their whole genuine equivariant structure, I could still understand the full topological cyclic homology, and then discussed it with Thomas Nikolaus, and he saw that maybe you have to put some hypotheses in, but it basically works. But yeah, this was some kind of eureka moment that I finally understood what this topological cyclic homology is in a way that made some sense to me. I don't know. Yeah, I was involved with this formalization, or not so much with the formalization itself, but there was this liquid tensor experiment formalizing the theorem of Dustin-Clausen and mine. And I had a lot of fun in the chat room where these people were active and discussing this. I never actually used Lean myself. And after this project was finished, I also didn't, I'm not involved in this community really anymore. I do think it's really quite impressive what what they're able to do. And I also think it's it's not something I want to personally do, but I think it's some kind of fun. But where this is headed, I don't know. I mean, something that I actually realized towards the end of this formalization is that it cannot really give you full confidence, I don't think, because like at some point they formalized the theorem which was about some kind of something condensed and some Banach space and whatever, and then they proved that with the definitions they set up that some X groups vanish. But one trivial way in which this would have been true is if they secretly defined all their Banach spaces to be 0. And yeah, so then you have to check that really the definition of Banach space is what you think a Banach space is. And like, yeah, at some point I really try to, at some point they tell you, well, now you just have to check all the definitions that they say what you say, and you don't have to check the proof anymore. But even I try to do that task a little bit for the liquid tensor experiment of checking all the definitions, and then I realized it's just impossible because even that is too much code, and they're all like these little syntax tricks that they probably use somewhere. So I mean, I'm not sufficiently fluent in this lean syntax to really be able to judge whether this definition does exactly what I think it does. So I felt that if I were to actually use a lean formalization in order to convince myself that it's true, I would probably still have to like process the proof myself. But okay, maybe I'm being overly. Well, I don't know. I mean, maybe I don't know. But yeah, so I don't have a clear vision where this formalization will lead us. But good question. Probably I kind of started being on like a mathematician track too early in my life to really have a likely alternative scenario where I wouldn't study mathematics. But I mean, I was never sure whether I would succeed in academia somewhere, but so my plan B was always to become a high school teacher. Nothing special really. So I don't know, between having a family, doing mathematics, and everything that involves also in like institute life and whatnot. I'm finding it hard to find time for hobbies. I like to listen to some kind of music and go to concerts sometimes. Oh, I know. I mean, I think collaboration is something extremely personal, so I wouldn't have any general advice. And I mean, I'm very open with ideas, so I just share ideas widely, and then sometimes people just approach me, hey, I would like to work out some ideas, or so I don't know. If you're very secretive about your works, then probably you're not having many collaborations. But I don't know. Yeah, so for example, one of my close collaborators is Bhagav Bhatt, and this actually started because he approached me that he would really like to work out this idea that there's this pro-étale site. I mean, I introduced this in the case of rigid varieties, and it was kind of clear that there should be some more elementary version that works for schemes, and that this gives a slightly cleaner language to talk about some things in étale cohomology. And I was kind of surprised because he's also a very strong mathematician. This was just some kind of project without any strong interest. I mean, it wouldn't prove any strong theorem. It's just some fun. But he still approached me that he would like to work this out with me, and I had a lot of fun working with him on it. Later, this paper did turn out to be much more influential than we probably realized it would be at the moment, because it was like the first, in some sense, condensed mathematics was born there in some sense. An anecdote here is actually that when Dustin Clausen saw this paper of Bhargav and mine on arXiv, he was kind of very confused why these strong people would suddenly write such boring papers, and he thought very lowly of the Proital site, he told me. And he actually then later on independently came up with this condensed formalism. And I actually had to convince him that he was just reinventing the Proital site, because he thought this is not something else. But yeah. So none of us really at first realized that there's something quite interesting there. Yeah, and then I mean, I just had so much fun working with Bhargav that we just ended up writing. I mean, we ended up discussing a lot of mathematics together, and then writing many papers together. And then there are other collaborations, such as the one with Zaghi, which really just came from this coincidence that we both happened to look at this kind of same thing, the Habir ring of number field, and then try to, like, coming from very different angles and trying to find some common ground. I don't know. Also fun was Thomas Nikolaus, actually also knew still from my early study days. We were at some summer academy together where he was actually still doing his studying theoretical physics, doing some work more or less in the direction of string theory or something, I don't exactly know. I was very much a number theorist, and then, I don't know, 5 years later in life or something, we ended writing a joint paper on algebraic topology, so that was fun. There's so many mathematicians always around, knowing all sorts of areas, and whenever you have any kind of question about some area of mathematics, probably at T, so we have T every day at 4, where everybody at MPIM goes and just chats a bit, and you can just ask the random expert about what you're interested in right now. And yes, it's just there's mathematics everywhere at the institute. You breathe mathematics. Yeah, it's great.